Hello everyone, myself Swami Pranod Dayanand and I am discussing the VHDL description of combinational circuits. So let's begin. What is VHDL? VHDL is one of the commonly used hardware description language in digital circuit design. VHDL stands for VHSIC Hardware Description Language. In turn, VHSIC stands for Very High Speed Integrated Circuit. Scope of this language is VHDL is suitable for use today in the digital hardware design processes from specification through high-level functional simulation, manual design and logic synthesis down to gate-level simulation. VHDL tool usually provides an integrated design environment in this area. So there are many features. Features of VHDL are it is worldwide popularly used language. So it support different types of modeling. There are first is structural, second data flow, third behavioral, fourth is mixed. Okay. Also VHDL can be used as a different complexity level from signal transistor up to complete systems and everything remains the same simulation environment. Okay, everything remains same in the same simulation environment. This language also supports flexible design methodologies, that is from top to bottom and mixed also. The language can be used as a communication medium in different CAD and CAE tools. These two tools are used mainly in the VHDL codes. So this language supports hierarchy, that is digital system can be modeled as a set of integrated components or subcomponents. This system supports this system or this code supports synchronizes and asynchronous timing models. Again, this also supports the test benches to write within it. There are different code styles of VHDL, or we can say that modelings. Okay, data flow, behavioral, and structure. So first, data flow. Data flow modeling makes use of the functions that defines the working of the circuit instead of its structure. So mainly we are discussing here is we mainly focus on the flow of the data from input to output. That is the data flow modeling style is mainly used to describe the combinational circuits. Here is an example for data flow modeling. Here I am taking the architecture that is data flow for a NAND gate. We have in VHDL we have NAND as a already predefined keyword, and if we use this keyword in between two operands, then directly the NAND operation is performed on those two variables. Let's begin. I am assigning X variable as a NAND of A and B and ending the data flow architecture. So let's go through this truth table. Here we can say that for NAND gate, it's a inverter of a AND gate. So here the NAND operator in VHDL performs the NAND operation. That is, this is the keyword which is used in the VHDL and it performs the NAND operation, producing output 1 only when the both inputs are 0. Okay, otherwise produces 0 output. Okay, so I am assigning X as less than or equal to a NAND of B directly implements the NAND logic operation because NAND is a predefined keyword inside this VHDL language. Therefore, the output X is 1 only when inputs A and B are 0, otherwise the output is 0. The truth table is I have shared, so you can go through it. Similarly, another model is their behavior modeling. So in this style, the behavior of the entity as a set of statement is executed sequentially. This behavioral model basically follows the sequence to execute the code in the specified order. Okay, only statements placed inside the process block or a function block or a procedure block are sequential. That is, process functions and procedures are the only sections of the code are executed sequentially. One important aspect of the behavior code is this is the not only limited for the sequential logic. Indeed, it helps uh, for also for the combinational circuits. That is, it works both on the combinational and sequential circuits, but it executes the code sequentially. That is the main thing which followed in the behavioral modeling. Here is an example for behavioral modeling. Here I am declaring the architecture behave, that is, it is a behavioral model of the NAND gate. I am just taking the NAND here. Okay, so within the begin block, I am taking the process with the code which is present inside the process is executed sequentially as we explained before. So the process of A and B is beginning as if A and B both are 1, then only Z is assigned to 0. We can say a truth table. Else assign the Z to 1 and end of this if block and end the process. This process which is performed on A and B is performed or executed sequentially, that by checking whether A and B are equal to 1, then only we are assigning Z value to 0, else assign Z to 1 in all these combinations. So I am ending this behavior model, that is architecture, which I have declared. Same the description or explanation I have explained in this slide. Okay. So next is structural modeling. In this modeling, an entity is described as a set of interconnected components. That is, we basically have two bodies or two components of this structural modeling. That is declarative, which before the keyword begin, which we are declaring, is the declaring part, and the next is statement part, which comes after the begin keyword. So let's see. Here is an example on it. Here we can see this code I am already declared, and before begin, which is there, this is a declaring part, and after begin, which is there, that is a declaring part. So I am declaring all this. I am doing here is I am uh, performing the NAND operation on A and B. So I am first declaring AND gate with the ports and the components of the A and B, and again I am again another one I am declaring inverter, which is nothing but the NOT gate. So if I perform the AND operation in a structural and I invert the outputs of the AND gate, then I will get the NAND gate. So similarly, the AND gate implements the logic of NAND gate, where the output of AND gate is 1 only when both inputs are 1. We know that already, that AND gate output is 1 only when the uh, output is 1 only when both inputs are 1. Similarly, if I apply invert gate to the AND output of the AND gate, so we can get the output of NAND. Okay. So similarly, I am performing this only operation inside the this code. Okay. So move on to the next. I have logic operation, that is basic gate known as AND gate. VHDL code. I am here. We can see that library IEEE is implemented or uh, called. So IEEE, this library contains all the modules which are required for the execution of the code or the behavior or structure, or we can say that execution of the code. So using IEEE, I am using the logic dot all. Means whichever I use keywords, I want to implement all those modules through this IEEE library. Entity, what is the entity? And one. That is this is just a variable, and yet I am performing. So and is the entity is port. What are the ports? X, Y are input ports. Okay, which are in the form of bits, that is 0 or 1. Okay, similarly Z is the output port, where it is also in the form of bit. End of the and this entity, what is the declaration I have completed here. Now the architecture is virat of and A. That is whatever I have declared, I have to begin and end that virat, that is architecture I have to declare here. That architecture is Z, which is the output, which should be less than or equal to and of A and B. And is a basically keyword inside the VHDL that performs the AND operation. So directly I am assigning. So what is AND? If both the output inputs are 1, then only I am getting the output as 1, or else I have to get the output as 0. So this is the logical symbol of the AND gate, and this is truth table and waveform. When see here, x and y both are 0, output is 0. If x y both are uh, either of x and y is 1, then the output is also 0. If both the inputs are 1, see here, both the inputs are 1, then I am getting the output z as 1, or else it is again 0. This is I have already written in this VHDL code. Similarly, we have OR gate. There is nothing different, just we have to vary the keyword, that is OR. Similarly, library we have to import because we need to perform these operations, and these are inbuilt inside this library. Okay. Using IEEE, I am importing all the modules which are present in the library IEEE. Now I am again declaring the entity OR as OR gate. Okay. we, Similarly, here also there are input reports which are x and y as input ports, which are in the form of bit form 0 or 1. Similarly, z as output, it is also bit form. Ending this OR entity, again the architecture, within this architecture I am declaring beginning z is equal to, which is nothing but output of this OR gate is equal to x or y. That is, when there is a both inputs are 0 0, then I have to get the output as 0, or else either of the input is 1 or both the inputs are 1, then I have to get the output as 1. This is the logical symbol of the OR gate. Similarly, here I am providing the waveform. Okay, when x and y both are 0 1, I am getting the output as 1. Similarly, 1 0, I am getting 1, 1 1, I am getting 1. Okay, or else 0 0. If both are 0, I am getting the output as 0. Okay. Now logical operation on NOT gate using the VHDL. VHDL, similarly, I am importing the library IEEE using all the modules of IEEE. That in this entity I am using ports. Here we know that NOT gate has only single input, single output. So that is, here is the logical circuit diagram, that is single input. A as input, Q is the output. Here let's see ports. What are the ports? X is the input port, which is in the form of bit 0 or 1, and single input, and output is z, that is single output as a bit form. Okay, then architecture we have to begin like z is less than or equal to not of x. Not is already inbuilt inside this library. I am importing all the modules. Then not of x is nothing but z. Similarly, if x is 0, z has to be 1. If x is 1, z has to be 0. Similarly, let's see here. X is 1, z is 0. X is 0, z is 1. So this is performing the inverter operation, that is not gate. Again, I have logic operation for NAND gate because this presentation is mainly using VHDL for introduction for VHDL code. VHDL here similarly for NAND is similarly I am importing IEEE library. I am importing all the modules and declaring A, B as input ports, C as the output port. C, I am assigning C as equal to A, NAND of B. NAND is already the keyword I have explained before. Inside this, I have VHDL code itself, and I am getting the output. Okay, this output is nothing but inverter of the AND gate. This is the logical symbol. This is the waveform. We can say that. Okay. Next, it is a operation for NOR. Similarly, nothing different. Same, all two input, single output. I am assigning a NOR of P. NOR is also here keyword, and we can see here output is nothing but inverter or not of OR gate. Okay, logical symbol for an OR gate and waveform. So Next is XOR gate. In VHDL, XOR is also already also the inbuilt function which perform the XOR operation. Okay, ports are AB inputs, C as output, C assigning as A XOR of B. I am getting the output. That XOR, we know that either the input is 1, then we get the output as 1, or else the if both the inputs are similar, we will get the output as 0. This is the logical symbol for a XOR, and this is the waveform. Okay. Similarly, next one we'll move to the XNOR gate. XNOR here, let's see. Similarly, I'm importing library using all the modules. Ports are similarly A, B as the input port, C as the output port. I am assigning the same C as output port to the XOR. Here, XNOR, in XNOR, if we have to write code for XNOR in the VHDL, there is no XNOR as a keyword inside this library. So I am taking what? Not of the XOR gate. Will get the output. That is, if both the inputs are similar, then I will get the output as 1. Else, either of the input is 1, then I will get the output as a 0. Okay. This is the logical symbol for XNOR. Okay. And the waveform I have provided. This is the combinational circuit. Basically, I am taking the example for combinational circuit, that is half adder. We know half adder, which performs the adding and expression. Okay, so here we have two inputs and two outputs. Two inputs and two outputs. Two inputs, the output we can get in the form of sum and a carry. Okay, so VHDL code. I am explaining the code. Let's see. Library, I have imported IEEE. I am using all the modules of IEEE in entity of half adder as a variable. I am declaring the ports as A, B as a input port. Okay, bit form. Similarly, sum and carry are the output ports. Let's see. We have two output ports. So let's see. Begin. If sum is nothing but inside the half adder, sum is nothing but the XOR between the two inputs, and carry is nothing but AND gate of the two inputs. Okay. So similarly, based on these operations, we'll get the output in this truth table. Let's see. Sum XOR is nothing but what? If either the input is 1, we are getting the output as 1, or else the output is 0. Similarly, we got here. And carry. And is nothing but when if both the inputs are 1, we are getting output as a 1, or else all the outputs are 0. Similarly, all data I have got in this half adder as a combination circuit. Here, this is a logical circuit diagram for the half adder. What is the sum? Sum is nothing but the XOR of A and B. We know XOR gate. Okay, this is XOR gate, and the sum I got as output. And what is the carry? Carry is nothing but AND of A and B. AND gate I have already used. We can also do here by without using this XOR gate. By using basic gates, we can also write the logic circuit diagram and see here the waveform. Waveform is nothing but A, B both are input, sum and carry are output. If A, B 0, 0, I am getting sum as 0. If 0, 1, I am getting sum as 1. 1, 0, sum 1. Carry is remains 0 because carry is nothing but AND gate. So we have to get output 1 only when the both inputs are 1. Okay. Similarly, we have got the waveform, and thank you for this.